2.2 is looking at the square root of a function. So what we're going to do for the first part here is just compare the graphs of what a linear function looks like and what a square root function is. And again, this isn't new. We've done in Pre-Calc 20 and then also a little bit in the last unit when we were looking at transformations. We looked at square root functions. So it says, given that f of x is equal to 3 minus 2x, we want to graph the functions of y is equal to fx and y is equal to the square root of fx. So 3 minus 2x, and I've done a table of values for this. You could have just as easily did your slope-intercept method and plotted it. Or sorry, I didn't do it. This was from the example. But you could have done just a slope-intercept method. But I want to have coordinates to compare. So that's why there's the table of values. So when you plug in your values of -2, -1, 0, 1, and 1.5, you get your y values of 7, 5, 3, 1, and 0. So the square root of that is just simply taking the square root of your answer that you got for the y coordinate and square root those values. So you get square root 7, square root 5, square root 3, 1, and 0. So when you draw those, the linear function is the blue line, and the red line is the square root of that function. So it says, for y is equal to fx, the domain is all real numbers, and the range is all real numbers. So for our straight line, domain and range, we can put absolutely any value that we want to in there. For the square root of the function, the domain is between, sorry, not between, is everything less than or equal to 1.5, and the range is everything greater than or equal to 0. So if I take a look at what I have here, my x values never went beyond 1.5, and my y values never went lower than that 0. On this graph we have invariant points, and if you remember, invariant points are the points that are the same between your two graphs. So these invariance points occurred at 1, 1 and at 1.5, 0. So they're common to both of those points. Sometimes you'll have one invariant point, sometimes you'll have two. So things to keep in mind when you're graphing the square root of a function. If the function is less than 0, so y is equal to square root of fx then is undefined because you can't take the square root of a negative number. So in your original equation, if it was a value less than 0, you can't square root it. So up in our table of values here, on purpose, we didn't have any y values less than 0 because the y values would have been negatives, and then we couldn't have graphed them. And if we do, then we have what we call or what we would put is the asymptote. So if the function is equal to 0, then y is equal to the square root of that function, and y is equal to fx will intersect at the x-axis. So if you take a look here, on this point, I don't know why I've got at this point here, my function equaled 0, so the square root also equaled at 0, and 1.5 and 0 would be an x-intercept. So that happens, if it's an x-intercept, it happens right here on the x-axis. And you can see the two graphs, that's where they intersected, they crossed at that point. If your function is between 0 and 1, then the square root is going to be above y is equal to fx. So do I have any between 0 and 1? I have at 1. So anything that is in between here, I'm going to just change my color. So between this point here and this point here, my graph, or my fx value here, this is the same number as the fx, so your y, would be between 0 and 1, so between these 2 points. So that means when your function is between 0 and 1, then your graph is going to be above your original line. If the function is equal to 1, then y is equal, or then your two functions will intersect. So they intersect if your function is equal to 0 or if your function is equal to 1. Those are two key things that you need to remember, because those are going to be what we call our invariant points. When you're drawing your graph and it just asks you to sketch it, you're always going to look for your x-intercepts, or your graph's intercepts, and then you're going to look for your invariant points when the function equals 0 and when the function is equal to 1. Yep. I'm just going to write that here, and we'll do more with invariant points as we go along. Okay, and the last one is if your function is greater than 1, then your graph is going to be below, or your square root function is going to be below the original function. So if we look here, wherever fx was greater than 1, so here at 0, 3, negative 1, 5, negative 2, 7. So all of these points here, from here on, coincide with this. And you can see those points on my square root function are all below my original function line. Okay, so key things there. If it's less than 0, you can't draw it. That's an undefined point. If your function is equal to 0, you have an invariant point. If it's between 0 and 1, then you're going to have that part of the graph curving above the line. If it is equal to 1, that's another invariant point. And if it's greater than 1, then it's going to go below the line. Okay, so given gx is equal to 3x plus 6, graph the function of y is equal to gx, and y is equal to the square root of the function. Just going to pause here for 1 sec. Okay, sorry, I almost deleted my recording there. So we're going to graph these two functions. So the first thing that we want to do is we want to just grab the function that we're given, not the square root, but just the function. So step number 1 here is to graph our function. So if we look at this, we know our slope is equal to 3 and our y-intercept is equal to 6. I don't have a put an axis on there so you can see what we're doing. Okay, so our first one is at, y-intercept is at 6. Always label. And our y-intercept is, or our slope is 3. And I would do your rise and run in both the positive and the negative. So I rose 3, went over 1, so now I'm going to fall 3 or go down 3 and over 1. Draw my line, and this is where it's a good idea to, I don't know what line that's going to give me, but we'll try it. When you're doing this, to use a straight edge so that your line is crossing exactly at the points, because then it's easier to figure out invariant points and such. No, that's not the type of line I wanted, but it'll work for now. Okay, so I'm just going to pretend I've got a arrow at the end there. Okay, so that's our first line. So the second thing that we want to do is we want to find our invariant points. And those are when your function is equal to 0 and it's equal to 1. Okay, so another way to write this is when function equals 0, function equals 1. So that's just simple substitution. So I have 0 is equal to 3x plus 6. So I have negative 6 is equal to 3x, divide by 3. Negative 2 is equal to x. So your one invariant point is going to be at negative 2, 0. Your other one will be 1 is equal to 3x plus 6. If I subtract 6, I have negative 5 is equal to 3x. So negative 5/3. And 1 is your other invariant point. So the thing to keep in mind here, then, is these invariant points this is where the curve is going to, we'll say, happen, okay? Basically, between those are our two invariant points, then the curve's going to either be going up or down depending on the graph at those 2 points. Okay. So the next thing we want to do is we want to find our y-intercept. So where is our square root function going to cross the y-axis? And you could find the x-intercept too, however, we don't need to for this one. So to find the y-intercept of y is equal to the square root of gx, because we know what it is from our line, it's at 6. We just substitute it, so we're going to do, to find the y-intercept, you let x equal to 0, so y is equal to square root of 3 times 0 plus 6. So square root of 6, which is approximately 2.5. So it's going to be at 0 and 2.5. So I graph this. My invariant points were at negative 2, 0. So right there. And negative 5/3 and 1. Where's negative 5/3? Negative 5/3, so negative 5/3 is almost 2 and 1, so right about there. And then for my other x and y values, then this graph is just going to go like that. And I probably have a little bit too much. Oh, no, I need to do I do have too much of a curve, because my y-intercept was at 2.5, so here's 1, 2.5. Whoops, should be red. So it's going to go like that. Okay, it says identify the domain or range of each function and any invariant points. So for a regular function, the domain and range are all real numbers. For the square root function, our domain is the set of values for x such that x is everything greater than or equal to negative 2. We never went past negative 2. Sorry, that should be a negative 2. And our range, our y never went below the 0. And of course, they're elements of real numbers. Okay, our invariant points we already identified as being -2, 0, and -5/3 and 1. Okay, example 3 says identify and compare the the domains and ranges of the functions y is equal to x squared minus 1 and y is equal to x square root of x squared minus 1, and compare your answers. So for the first one, y is equal to x squared minus 1. Our domain, I can put any x value that I want in there. And the range then will be all real numbers as well. I can't substitute 0 in there, and I can't and if I use the value of 1 or -1, so 1 squared will give me a 0, square root of 0. If we go back to here, we're going to get an invariant point for it. So you can still use those values, but between 1 and -1 are going to give you some invariant points. Anything else that you put in there, though, will give you a value. So if I used a -2 squared, then I'm going to have 4 minus 1. Oh, I can do the square root of that, just like I could do this 2 squared minus 1 will be 4 minus 1, so it gives you the same thing because of that squared in there. Okay, using the graph of y is equal to hx, sketch the graph of y is equal to the square root of hx. So I want to look at a couple of key points. First thing that I want to do is I want to find my invariant points. So remember, that's when my function is equal to 0 and to 1. So my function is 0. When y is equal to 0, x is equal to -2, and when y was equal to 1, which is up here, my x was equal to 0. So the invariant points are at -2, 0, and 0 and 1. So that's where the curve is going to happen. So I'll put my invariant points on there here and here. So then what you want to do is you want to pick a point on y is equal to hx. Okay, so I'll just write that down. So you pick a point, whatever, on the original graph. So for this one, let's pick this point here, 2, 2. So if we take a look at then, y is equal to square root of hx. If we use the point 2, so when x is equal to 2, y is going to equal the square root of 2. Because remember, this is my x and y, or this is the same as h of x. So I could have picked another point. I could have picked 4 and 3. So then I would have substituted when x is equal to 4, y is equal to square root of 3. So when I solve that, 2 is almost equal to 1 and a half. So this would be at the point 2, 1.5. So then you can pick a second point. So my second point is going to be, well, let me do that 4, 3, okay? So I'm going to use second point of 4, 3. So when x is equal to 4, y is equal to the square root of 3, which is approximately 1.7. So this is the point 4, 1.7. So then you plot points and sketch the graph. So my other points were at 2 and 1.5, so about right there. And then another point was at 4 and 1.7, so about there. So my graph curves up here and continues like that. So that's all there is to graphing it. So it says use the graph of y is equal to gx to graph y is equal to square root of gx. So now I have a parabola, so I know that my function is going to be squared. Same steps are going to apply. First thing that we want to do is find our invariant points. So when y is equal to 0 and when y is equal to 1 on our original graph. So on that graph, when y is equal to 0, x is equal to right there, so about 1.5. So it's at 1.5 and 0. And when y was equal to 1, we're here. We have 2. There's one there, and there's one there. Sorry, and there's also 2 here. Oh, and I wrote the 1, but I didn't write the other, negative 1.5 and 0. So when y is equal to 1, we have negative 2 and 1, and we have 2 and 1. So we have 2 sets of invariant points. So now you pick a y coordinate on your original graph gx. And and it doesn't really matter which point you pick, but if you pick a point that is a perfect square, then at least you're going to be able to square root that one. So if I pick this point, so we're 4, I'm going to pick this point here and this point here. So on my gx graph, I have the point, what is that, about 3.2, we'll say. And then there's also over here, which is at negative 3.2 and 4. So when x is equal to 3.2, y is equal to the square root of 4, which is 2. Or when x is equal to negative 3.2, y is equal to square root of 4, which is 2. So then that means I have a point at 3.2 and 2, and then I have another point at negative 3.2 and 2. So if I plot those, I'm going to make my invariant points, red. And then my other points were at 3.2 and 2. So about right there. That's kind of over a little bit more. And then negative 3.2 and 2. So there and there. And if you're wondering, well, should I have gone this way? The thing to keep in mind is on that first page, when your y values are greater than that invariant point, then you're graph has to be below. So when I'm at 2, when y is equal to 2, 4, and so on, my graph has to go below. So that's why there. That's why my graph curves in those directions. Okay, and then the last little bit here is just your key ideas. It says you can use the values of the function of x to predict the square root of the function and to graph that function. So the key values to remember is when your function is equal to 0 and when your function is equal to 1, or y equals 0, y equals 1 if you're looking at a table of values. So those are going to give you your invariant points. The domain of y is equal to the square root of function consists of all the values in the domain of the function for which the function is greater than or equal to 0. So you can't put a negative value inside that square root. It's basically what it's saying. The range of y is equal to the square root function consists of the square root of all the values in the range for which fx is defined. So if you have any points that you substitute in there where fx is not defined, so like a negative value, then your square root of the negative value, then you can't include those. The y coordinates of the points on the graph, y is equal to the square root of the function, are the square roots of the y coordinates of the corresponding points of the original function. So basically all that's saying is just what I did with those points. I picked those points 3.2 and 4. So the y coordinate is just the square root of that y value in the original function.